When Voyager 2 flew past Neptune in 1989, we got the sharpest view of the planet ever taken. Giant telescopes on the ground and even Hubble and the James Webb Space Telescopes can't match what Voyager saw on its flyby more than 3.5 decades ago. The only problem is that Neptune doesn't look like this. It's actually a false color image. In fact, the Voyager team even said as much when they announced the image to the press.
The image on the right is enhanced, and the enhancement process unfortunately gives the planet a color which is a bit stronger than it really should. It gets a bit bluer and the hue gets a bit stronger, but it is a consequence of that enhancement process, and so we'll be seeing it like that from time to time.
Yeah, we're going to be seeing it from time to time, like for the next 35 years. You could even see right there that they had an unenhanced image of Neptune that looked closer to what the human eye would actually see. But it's the false color image that we see everywhere, and the vast majority of people have no idea what Neptune really looks like. But now a team of astronomers used data from the Hubble Space Telescope and the Very Large Telescope to reprocess Voyager's images of Neptune and Uranus, and now show how both planets would really appear to the human eye. This is the handiwork of a team led by Professor Patrick Irwin from Oxford University. What's funny about this is that they were actually trying to understand why Uranus's color changes during its 84-year orbit around the Sun. So today we're going to talk about how the deep blue false color image of Neptune became canon, how the research team reprocessed Voyager's images of Uranus and Neptune, and what they learned from it. Now, I get nostalgic for Voyager 2's Neptune encounter because I was working at the telescope at Villanova University on the night of Voyager's flyby. I even brought in a TV set to watch Neptune all night on PBS, and yeah, I even set the TV right up along the southwest wall so that I could kind of look up toward Neptune, even though I couldn't actually see it, and I did it anyway because I'm a nerd. Anyway, a few months later, we all got together in the astronomy department to watch Neptune's Cold Fury on PBS, hosted by none other than Sir Patrick Stewart.
Hello, I'm Patrick Stewart. As the actor playing Captain Picard of the Starship Enterprise, I have journeyed to some very distant places. But tonight, I'm going to take you to two worlds, as strange as any I've visited on Star Trek: The Next Generation.
And that's why I'm so happy to thank Star Trek Fleet Command for sponsoring this week's video. Star Trek Fleet Command is a 4X MMO game set in the ever-expanding Star Trek universe. Recruit legendary characters to crew ships from over 50 years of Star Trek and send them on missions of exploration to expand your territory. Build powerful ships, including the USS Enterprise, the Romulan Warbird, and Klingon Bird of Prey. Engage players around the world in battles, testing your strategic abilities, negotiate alliances for greater gain, and harvest the galaxy's resources as you upgrade your fleet of starships. Even better, Star Trek Fleet Command is a cross-play game that is available on desktop and mobile with a Scopely account. So you can play at home and seamlessly continue your game on your phone when you're away. And best of all, the game is free, with new events and content being added every month. If you're a Trekkie like me, I think you'll really get a kick out of Star Trek Fleet Command. You can get the game for free by scanning my QR code or by using the link in the description. And if you're new to the game, then make sure to use my special promo code WARPSPEED to get a content pack for free. And now let's boldly go back to the video. To understand how we got these false color images of Neptune, let's first talk about how Voyager actually creates the images. Voyager doesn't take color images per se, but rather takes a sequence of grayscale images seen through a set of filters ranging from ultraviolet to orange light. To produce color images, you assign red, green, and blue colors to their respective filters and combine them. The result is an image that's pretty close to what the human eye would see, but not quite exactly. And that's because Voyager's red, green, and orange filters aren't a perfect overlap with the red, green, and blue receptors of the human eye. So technically, even the true color images aren't exactly what the eye would see, but they're close enough. But those images can be further enhanced, and that way you can bring out details that would otherwise be hard to notice. However, enhancing the images like this changes their overall appearance, including their color. Voyager's images were processed at JPL's Multi-Mission Image Processing Laboratory, or MIPL. Although they released natural, or at least close to natural, color images of Voyager's previous flybys of Jupiter, Saturn, and Uranus, they also distributed false color images as well. And guess which ones got published? Yeah, those funky colored images were everywhere. On TV, in magazines, even in black and white in the newspapers. After all, they were cool, they were colorful, they were spacey, and besides, it was the 1980s and people dressed like this. But behind the scenes, planetary scientists were becoming increasingly concerned. False color images are a staple in astronomical imaging. That's how you learn about the makeup of a planet. But seeing those false color images going out as press releases was misleading the public into thinking that that's what those planets actually looked like. Sure, they may have had a caption explaining that they were false color, but what were the chances that anybody would really notice? With the final encounter at Neptune approaching, planetary scientists begged MIPL to not release any false color images this time. Unfortunately, MIPL released only false color images of the full disk of Neptune. Now, I have no idea why they didn't release a natural color image, but in fairness, I can imagine a couple of reasons why they wanted to release the false color ones. First, Neptune turned out to be a wonderful surprise. At 30 astronomical units from the Sun, Neptune receives less than 1/10 of 1% of the sunlight we get here on Earth. So it was widely assumed that this would be another quiet planet, much like the way Uranus appeared to be 3 years earlier. But since Neptune turned out to have all of these cool storms like the Great Dark Spot and other features, I'm sure MIPL just wanted to show them off to the public as best they could. And even if the deep blue color was just an artifact of image processing, at least it had the added benefit of helping the public to distinguish Neptune from Uranus. But no matter the justification, that false color image became the canonical image of Neptune that shows up in every video, every documentary, every planetarium show, you name it. For the vast majority of human beings, Neptune is a dark blue planet. So why would it take all of this time to finally get the Voyager images into true color? Well, it actually hasn't taken quite all this time. It's been reprocessed before to strike a more natural color balance, but this new work by Irwin and collaborators goes a huge step further to create the most accurate color images of both planets to date. Now, Irwin's team were actually trying to understand why Uranus, not Neptune, changes its color as it orbits the Sun. The weirdest thing about Uranus is that it's tilted by 98 degrees. So rather than thinking of it as spinning like a top as it orbits the Sun, it's kind of rolling around on its side. When Voyager flew past Uranus in 1986, it was shortly after its southern summer solstice. So its south pole was pointed more or less directly toward the Sun. Uranus also turned out to be featureless. There were no clouds, no storms, really nothing seemed to be going on. But the false color images revealed a darker polar hood surrounded by a series of progressively lighter concentric bands. It was thought that this hood might be some kind of haze or smog that was concentrated over the pole. Now, despite its appearance in false color, the polar hood was reflecting more light than the lower latitudes. So whatever the hood was, it seemed to be made of some kind of brighter material than the rest of the planet. Fast forward to 2007, when Uranus reached its equinox. By this time, Voyager was long gone, so the best observations we could make were with the Hubble Space Telescope. This time, Uranus appeared quite a bit different. The bright polar hood seemed to be smaller, and that meant the polar region wasn't reflecting as much light as it was during the solstice, and that made the planet appear a little darker and bluer. These observations were further evidence that Uranus seems to undergo changes in its color and brightness with the seasons. But exactly how those changes come about remained unclear. To figure that out, the research team needed to first nail down the true colors of both Uranus and Neptune, and then compare how both planets changed their appearance over the same time period. Now, you might think that should be kind of easy. You just assign the red, green, and blue colors to their appropriate Voyager and Hubble filters and combine them into full color images. But the problem is that Voyager's filters don't exactly overlap with Hubble's, and neither directly corresponds to what the human eye actually sees. So to get the ground truth on the colors of these planets, the team used a special instrument on the European Southern Observatory's Very Large Telescope called the Multi-Unit Spectroscopic Explorer, or MUSE. MUSE is a kind of instrument called an integral field unit. That means it doesn't just take images, but also the spectrum of each individual pixel in the image. And that allows each pixel's true color to be properly assigned and gives you a lot of color data of the different regions of each planet. Now, obviously, MUSE's images aren't nearly as sharp as Voyager's, but thanks to its precise color data, the team could go back and correct the colors for the corresponding parts on the Voyager images. Of course, it's much more complicated than that because both planets have moved over the last 35 years, and we're seeing them from different angles today than we did when Voyager 2 flew past. And plenty of storms and dark spots have come and gone in the meantime. But when it was all said and done, the team showed both planets as they would have appeared to you if you were riding along with Voyager. The planets are very similar in appearance, but Neptune is just a little more blue than Uranus. You can still make out features like the Great Dark Spot and some of its cloud bands, while Uranus still appears, well, kind of the same. Now, the team wanted to understand Uranus's seasonal changes. So by looking at data going all the way back to 1950 from the Lowell Observatory, they could compare that to the color-corrected data from the Hubble Space Telescope and use that information to confirm that at its solstice, Uranus was in fact a little brighter and greener, while at the equinox it was a little darker and more blue. The next step was to model Uranus to figure out what it had to do to create the changes that we see. Their models show that concentrations of methane gas were changing over the course of Uranus's year. Methane gas absorbs red light and even a decent amount of green, while at the same time reflecting more blue light. But when Voyager looked at Uranus during its southern summer solstice, there was only about half as much methane present in the polar region as there was in the rest of the planet. So with more red and green light being reflected from the pole, Uranus took on an overall greener and brighter appearance. But by the time Uranus reached its equinox, the methane at the poles returned to the same levels as the rest of the planet, and that allowed the planet to absorb red light at the poles and at the equator equally. With less red light being reflected back, Uranus took on a darker and bluer color. Now, compared to Uranus, Neptune doesn't seem to change very much at all, and that's for a couple of reasons. First, it's much further from the Sun, so its orbital period takes about twice as long as Uranus. So Neptune's seasons last about twice as long as they do on Uranus as well. Second, Neptune's axial tilt is similar to Earth's. So while Neptune does undergo seasonal changes, they're not nearly as dramatic as those on Uranus. The result is Neptune appears a little bit darker and a little bit bluer than Uranus, only just not nearly as blue as most people thought. I honestly don't know if these new images will correct everyone's perception of Neptune, but it warmed my heart to see that Wikipedia's entry on Neptune was updated with the corrected image. And you know who else warms my heart? My patrons, for helping to keep Launchpad Astronomy going. Thank you so much. I hope you'll consider subscribing and ringing that notification bell so you don't miss out on any new videos. Until next time, stay curious, my friend.